So good evening. Good evening and welcome to the latest installment of the SLAC Public Lectures. Today we're very happy to have Dan Wilkins, who's going to give a talk about black holes at the centers of active galaxies. So Dan received his PhD from Cambridge University, actually a famous font of wisdom on black holes. Then he took postdoctoral appointments in Canada at Halifax and at CETA in Toronto, also one of the major centers. After that, he won a NASA award called an Einstein Fellowship, which basically pays you for several years, and you can take it anywhere to go and work. And we're very lucky he chose to come here. And now he's associated with KIPAC, our Astrophysics Institute. He spends about half his time basically doing calculations of the structure of black holes, trying to figure out what black holes at the centers of galaxies are actually supposed to look like. And the other half of his time designing X-ray telescope satellites to go take those pictures to see if he was right. So in this talk, he'll tell you all about it. Dan, thank you very much.
Thank you. And good evening to all of you. It's a great pleasure to be here this evening. So from here on Earth, you might be forgiven for thinking that the night sky is a pretty calm and tranquil place. But looks can be deceiving. There are some pretty violent and energetic processes going on out there that can dwarf even the power of our own sun. Take the Cygnus galaxy, 20 million light years away. You see an image here taken from the Hubble Space Telescope. At first glance, it might look like a pretty run-of-the-mill spiral galaxy. We've got these arms of stars in the galaxy that we've become pretty used to seeing. But there's a monster lurking down here in the center of that galaxy. The center of that galaxy is glowing with the power of 100 billion suns. That is the energy output of an entire galaxy worth of stars compressed into a volume of space the size of our solar system. These are known as active galactic nuclei, which there's a whole zoology of terms that have come up over the years for those. You may have heard the term quasars and the like. That is one of these. These are the most luminous, continuous sources of light that we see in the entire universe. Though I say continuous there, I'm not counting supernova explosions and any sudden bursts of light. But if we're looking at continuous light sources, these are the brightest things we have ever seen in the universe. So this evening, we're going to find out exactly what powers such extreme systems and how we can study them. We're going to discover how they can give rise to fantastic firework displays. And we're going to see just how important a role they played in the formation of the universe as we see it today. So the first question we need to answer is, how can we power something that's this bright? Well, first of all, how bright even is it? Well, we can think about this in terms of Einstein's famous equation, E equals mc squared. And in a nutshell, what Einstein was saying in this equation is that energy, E, and matter, m, we can consider to be equivalent. You can kind of think about solid matter as being a sort of stored up, condensed ball of energy. And the amount of energy that's stored in it, you just multiply its mass, m, by c squared. So we'll take those 100 billion suns worth of power, put that into E, and it turns out that in order to get that amount of energy, you would have to completely consume, completely release the energy that's stored up in 300 times the mass of our planet Earth every single day to keep that bright light in the center of the galaxy alight. But that's assuming that we have some means of 100% converting that matter, those condensed up balls of energy, freeing every single bit of that energy into light. Of course, we can never be 100% efficient. So how efficient can we be? So what I'm going to do is I'm going to put a number, epsilon, here in front of mc squared, the total stored up amount of energy. This little epsilon here is just going to tell us what percentage of that we're able to get access to. And if we just try and run normal chemical reactions, so pretty much all the things we're used to on Earth that release energy, so lighting a fire, setting off some dynamite, we can only get 100,000th of 1% of that total stored up mc squared out. Nuclear fission, so nuclear power reactors or even atom bombs, can do a bit better. They can get 0.01% of the stored energy out. And nuclear fusion, the reactions that are powering our sunlight, can get 0.1% of the stored up mc squared. But the only process we know about that can get anything close to all of the energy that's stored up out is the force of gravity. So we can think about releasing energy by gravity. If I take this clicker and I drop it on the stage, what's going to happen as it falls? It's going to get faster and faster. So the gravitational pull of the Earth is putting kinetic energy into this, and then when it hits the stage, it's going to make a sound, and as it rubs against the stage, it's going to heat up as well. So we're going to release some energy by gravity. How much energy you can release by gravity depends on how much mass is attracting you down, how big the source of that gravity is, but also how close you can get to the center of that object. And it turns out that we can get up to around 40% of the stored up energy out just by dropping things under the force of gravity. But we need something very heavy and very small so that we can get close to its center. We need something incredibly dense. So what would that be? Well, the way we find anything in the universe, the way as astronomers and astrophysicists we learn about pretty much everything in the universe, is through the light that is sent to us. I'll add the caveat that a few years ago that statement became not quite true when we discovered gravitational waves for the first time. But traditionally, we learn about the universe from the light that is coming to us. And we can think of light as being a wave, a ripple. How big the ripple is, how high it goes, determines how bright the light is, and how quickly this rippling happens. So the frequency of the ripples, how close together in time the oscillations are, or alternatively the wavelength, the distance between consecutive ripples, that we can think of as being the energy of the light, how energetic the light is. And the energy of the packets of light that we receive, our eyes perceive as colour. So red light is the lowest energy, the slowest oscillation, up to the yellow, green, blue, and violet, which is the highest. But the visible light, the optical light that our eyes can detect, is just a small part of the total so-called electromagnetic spectrum of all the different types of light. So if we take the lowest energy light that we see, that's red, and we reduce that energy, we can't see it anymore, but we end up with infrared light that we can feel as heat. And going to lower energy still, we end up with microwaves and then radio waves. But in the opposite direction, we start with our high energy violet light, we give it more energy, we get ultraviolet, and finally we get up to X-rays and gamma rays. So to look for the most extreme objects in the universe, it makes sense to look for the most energetic forms of light that could be coming from them. We're going to ignore the gamma rays for today, because it turns out that gamma rays can't travel very far through space. Where you have a lot of gamma rays together, they tend to collide with each other, and then they make particles. They make electrons and positrons. So the gamma rays have a hard time getting to us. We do see some gamma rays from space, but what I'm really going to focus on today are the X-rays. But X-rays don't travel very far through the Earth's atmosphere. So if we want to detect X-rays coming from space, we need to put our detectors up above the Earth's atmosphere. So our story goes back to 1962, to Riccardo Giacconi, who was conducting rocket experiments in New Mexico. What he and his colleagues would do is put an X-ray detector into the nose cone of what's called a sounding rocket. It's a fairly small rocket here. That would then carry the detector up into the upper layers of the Earth's atmosphere. As it flies, the rocket would spin round, and that means the detector gets a scan over the whole sky. It then falls back down in the desert, you go find it, and hopefully you get some data. And these early experiments led to what was at the same time an embarrassing and incredible result. Whenever we look for a new type of light in astronomy, so when we're looking for X-rays for the first time coming from space, what we'll often do is look to the sun first. We're used to the sun being a pretty bright source of most types of light. But it turned out that the background sky all around the sun was brighter than the sun itself. There are these X-rays that are permeating the universe, brighter than the sun. Well, into the late 1960s and early 1970s, the detectors got better. And in 1970, NASA launched the Uhuru satellite, which was able to see that it wasn't a continuum of X-rays bathing the universe. Rather, a lot of the X-rays were coming from discrete point-like sources. So what we're talking about here are points of light, just like a star, shining, but instead of it being visible light, it's higher energy X-ray light. And one of these bright sources was found in the constellation of Cygnus. We can't see it with our naked eye, but using a modern X-ray telescope, we see this bright, point-like source of light right in the middle of the detector. Don't worry about the sort of the star shape and the lines on it. This really is just a point of light. It's just imperfections in the detector that cause it to spread out. This is a source imaginatively called Cygnus X1. Now, astronomers are really bad at coming up with names for things. So Cygnus X1 just means it's the first X-ray source that was discovered in the constellation of Cygnus. It's about 6,000 light years away, and it's between 10,000 and 100,000 times brighter than our sun is, but shining not in visible light, but in X-ray light. What could such a bright source of X-rays be? Well, after finding this object, astronomers, of course, followed up using traditional telescopes, looking with the visible light to see what was there. And they saw a pretty big star there, 15 to 30 times the size of our own sun. But stars don't emit X-rays in large quantities, just like our sun was dimmer than the sky around it. So it's probably not the star itself. Looking closer at that star, it wasn't remaining stationary. That star was travelling around in an orbit. There was something holding that star in orbit that it was travelling round. So let's go back to our force of gravity that I said could liberate huge amounts of energy. Could it be that whatever is tugging on that star, holding it in orbit, is actually ripping the star apart, pulling the gas off of it? Well, we can work out how big, how heavy this object has to be, just because we know this star's travelling around in orbit. So its gravity has to be strong enough to stop the star flying off into space. So this mysterious object down here has to be about 15 times the mass of our sun. The X-rays that come from this object also vary very rapidly. Imagine a light bulb flickering, getting brighter and dimmer. This thing is flickering on timescales shorter than 1,000th of a second. And that lets us learn something about how big the object can be. Because if I've got something here on the stage that's glowing, but getting brighter and dimmer, maybe getting hotter and colder, if the whole thing is going up and down in brightness together, it has to be small enough that in the time we see it flickering up and down, the information about it getting brighter and dimmer can travel from one side to the other. Because the whole thing has to know to get brighter and dimmer at the same time. It's causality. And information cannot travel faster than the speed of light. So if this object is varying faster than a millisecond, it can't be bigger than the distance light can travel in a millisecond. So it can be at most 100 kilometers in size, but 15 times the mass of our sun. So we're talking about something the size of maybe Northern California, but as heavy as 10 suns, 15 suns. How can we form something so dense? So let's go back to looking at that star. Well, throughout its entire life, a star exists in perfect balance. So the force of gravity is a mutual attraction between everything in the universe that has mass. Absolutely everything with mass is attracted to everything else with mass. And the more mass you've got, the bigger the attractive force. Now, it turns out gravity is quite weak, like for like. So you don't see my slide clicker being hurled to the gentleman in the third row by the attractive force of gravity, because gravity's not that strong. The only way we get strong enough gravity that we can feel it is with something big and heavy, like the planet Earth underneath us. But where you have a star, the force of gravity is attracting every single bit of gas in this star to every other bit of gas in this star. So it's trying to pull the star together. It's trying to shrink that star. It's trying to make it smaller and smaller and denser and denser. But we've got nuclear fusion happening in that star as well. That gas is hot. If you've ever tried heating up air in a sealed tin can, please don't try this at home, you might know that it can blow the lid off the can. So when you heat gas up, it pushes out. So this force of gravity from a star is counterbalanced by the force of the hot gas all pushing out. But that's all well and good until that star runs out of the fuel it needs to keep its nuclear fusion reaction going. When it runs out of fuel, the nuclear fusion stops, and it stops being able to heat itself up. So now we take away the outwards force counterbalancing the gravity. So now the gravity starts to win. That star starts getting pulled together. But you compress gas, it heats up. And if you've got a star that's 10 times the size of our sun, 50 times the size of our sun, even 100 times the size of our sun, that force of gravity really is pretty big. So you heat that gas up so much, as the star collapses down, the outer layers of the star get blown off in a supernova explosion. So the outer layers of this star now have got so hot, so much energy from the collapse has been put into that gas, it's blown it away. But there will still be something left in the middle that gravity can act on and start pulling it together. And that can form a neutron star. So we have what's left of that star after the explosion has blown the outer parts away. Gravity's pulling it in, and it starts to get squeezed. When you squeeze atoms, the electrons going around the nucleus and the protons in the nucleus can combine. And when that happens, they turn into neutrons. So what you end up with left in this collapsing remnant of a star is predominantly a ball of neutrons. And the laws of quantum mechanics say that neutrons are quite antisocial particles. They don't like sitting on top of each other. So if you try and push neutrons together too much, they'll start to resist, and they'll start to push back out again, unless you can overcome that force by squeezing them harder. So if you've got something less than maybe about 3 times the mass of our sun, providing that gravity pulling it together, the gravity is not strong enough to overcome the neutrons. So the neutrons will then hold the star up, and what we end up with is something a few times the mass of our sun, squeezed into a space about 10 kilometers across. That's about the size of San Francisco. Now, some of you, if you've read about neutron stars before, may have heard the number 1.4 times the mass of the sun, which was the traditional number. So 1.4 times the sun would be the limit to how much neutrons can push together if you just have a ball of neutrons. But when you start squeezing neutrons together, you can start getting exotic states of matter where instead of behaving as individual neutrons, they all start interacting with each other. We don't fully understand what happens here. This really is pushing our understanding of nuclear physics. But there's all these ideas of things called quark stars, where the neutrons all start behaving as one big object, and that can push the limit up to about 3 times the size of the sun instead of 1.4. Just if any of you have seen that number before. And a neutron star. In this image here, you see it's got these loops around it. And what these loops are is a magnetic field. Just like a bar magnet. If you ever put iron filings around a bar magnet and you see the lines of force, that's what you're seeing visualized around here. During its life, a star with all the hot gas swirling round can act like a dynamo and generate a magnetic field. And as the star collapses, that magnetic field starts to get focused in, it gets concentrated, and the neutron star keeps the magnetic field attached to it. And that's an idea we'll come back to a little bit later. So hold on to that thought of just having around our remnant at the end of the star's life a magnetic field, just like a bar magnet in the middle of it. Okay, so that's a star that can hold itself up, a neutron star. What happens if we've got more than 3 times the mass of the sun? Well, then there's nothing we know of that can stop the gravity. This object is going to get squeezed, it's going to get smaller, and it's going to get denser. And the force of gravity at its surface is going to keep getting stronger and stronger and stronger. And this is where we have the idea of a black hole. The idea of black holes in terms of having very strong concentrated gravity from a very dense object is nothing new. The idea was actually first coined by John Mitchell in 1783, who used the term dark star. And independently, the French physicist Pierre-Simon Laplace, about the same time, came up with the same idea. Now, they were considering the ability to escape from gravity. So if you have a ball on the planet Earth, if you throw it up, it'll fall back down. If you throw it up faster, it will get further, but it will still come back down. If you throw it up fast enough, it will be able to keep travelling out forever and escape the planet Earth. That's called the escape velocity. Now, we know that nothing can travel faster than the speed of light. So if the gravity is so strong that something travelling at the speed of light will still get pulled back, nothing can escape that gravitational pull. Not even light, hence the dark star. But at the time, there was no real theory of how gravity this strong could work. Newton's law of gravity doesn't provide for this. And it's worth mentioning, although the idea of black holes has been around since 1783, the word black hole actually came about in 1967 from John Archibald Wheeler. Well, the theory we need to understand gravity this strong is Einstein's general relativity. Now, for the mathematically minded among you, pretty much everything I'm going to say for the rest of the talk is in this equation right here. That is the entire theory, so if you understand that, you can switch off now. But what that equation is fundamentally telling us, actually Wheeler summed it up very nicely when he said that matter tells space how to curve and space tells matter how to move. That is what that equation means. So how do we curve space? Well, as humans, we can only think in 3 dimensions of space, 4 dimensions if you include time. So we struggle to visualize what a curve in our 3-dimensional space would look like. So what we're going to do is imagine a 2-dimensional universe, so a flat sheet. Now, if you live on our 2-dimensional universe, you can only move forwards and backwards and side to side. You can't move up and down. But Isaac Newton said that if you have a free particle, if you're not subjecting a particle to any force, it will keep travelling in a straight line. So, in our 2-dimensional universe, our free particle is just going to travel across in a straight line. But now, we're going to put something massive into the universe, a planet, a star. What happens is it creates a dent, if we now think of our universe as being like a rubber sheet. And now, our free particle is going to try and follow a straight line. But remember, it can't leave the surface. So if it tries to travel in a straight line here, it's going to fall into this dent, and it's going to be deflected as it rolls along. So what was a free particle, now, because it falls in the dent, its course changes. But of course, if you live in this universe, just like we live in this 3 plus 1-dimensional universe, we can't see the dent made by the planet Earth. All we see is the particle being deflected. So the curve in the universe looks to us like a force. And the same year that Einstein published his equation, Karl Schwarzschild solved the exact shape that a point of material would make in our 3 plus 1-dimensional universe. Now, 1916 was at the height of the First World War, and Karl Schwarzschild was serving on the Russian front in the German army. He completed this work in the trenches. Now, I struggle to imagine worse working conditions than that. So if we carry on with this idea of gravity being created by dents in our flexible space, the idea of a black hole drops out quite naturally. Now we've got something incredibly small and incredibly dense. It's going to create a very deep dent in space. If you're at a large distance, if we're sort of out here, it just looks like the same dent we had before. Black holes, contrary to what you've heard, do not suck. All black holes do is pull. If you're out here, pretty long distance away, it just looks like a normal dent in space. It just looks like normal force of gravity. You could deflect off of this in the same way as I showed that particle before. You'd come in and you'd escape again. But if you get to this point here, the curve in space becomes so steep, it's like falling down a well. Once you're there, there's no way to get out. Now, to get to this point, something the mass of the sun, you would have to be within a mile of its center. So you would have to compress the sun into just 1 mile across. And that's where this well would be. And this is called the event horizon. The event horizon is the point of no return. If you fall beyond that point, the only way you can possibly go is straight into the black hole. Now, even Einstein himself didn't think black holes existed. He thought they were just too weird. So it came to the astrophysicists of the 1960s, looking at that first X-ray data coming from space, to prove Einstein and even Stephen Hawking at the time wrong. Neither of them believed that black holes could exist. Well, by definition, we can't see a black hole because no light can escape its surface. Anything that falls in, all the light escapes. So how are we going to see one? If our star has gone through its big supernova explosion and collapsed into a black hole, how are we going to see it? Well, fortunately for us, most stars in the universe, unlike our sun, have companions. They're found in binary systems, so two stars orbiting around each other, or even triple systems. And yeah, the vast majority of them seem to be like this. So now we've got binary stars. We've got one sort of low-mass star that's sort of happily going through its life, living its life quite slowly. And we've got a big star here. This one is incredibly big. It's got an incredibly strong force of gravity pulling it in. It gets very hot, and it goes through its life extremely quickly. This star will run out of fuel. It'll explode as a supernova, leave a black hole. And the black hole that's left can gently tug on the surface of its companion. It steals the gas off of its companion. The gas gets pulled in, spirals around. The force of gravity keeps pulling it down and squeezing the gas together. As that gas gets squeezed together, it heats up to 1 million degrees. So that X-ray light that we were seeing in Cygnus X1 is this extremely hot gas. You might be familiar with heating something up. It'll start to glow red, and if you heat it up more, it'll glow yellow, it'll glow blue. If you heat it to 1 million degrees, it will go to the blue, to the ultraviolet, and then even start glowing in the X-rays. And it can also shoot out material at close to the speed of light in these amazing jets that we'll come back to later on. So, the anatomy of our astrophysical black hole, our black holes that we're going to study. Well, all that's left of the star is compressed right at the centre. It's been squeezed together in the singularity. Now, the neutron star, something a few times the mass of our sun in the size of San Francisco, that is between 5 and 10 times denser than the nucleus in the core of an atom. We've kept squeezing this into the black hole. So this is much, much denser than a nucleus of an atom. This can't be made of protons and neutrons as we're familiar with them. But unfortunately, we have no way of learning about what this material actually looks like because we've got the event horizon. No light, no information about what's in there can actually come out. So as far as we're concerned, we just have this very small condensed blob of star leftovers in the middle of the black hole. There's the event horizon. That's the point of no return. There's no light coming out from inside that point. And for a star that's come to the end of its life, like in Cygnus X1, this event horizon is about 10 miles away from the centre. But the more material you've got, the bigger this event horizon will be, the bigger the region of space that nothing can escape from. And then we have all of this gas getting heated up, glowing with X-rays, until it gets to what we call the last stable orbit. So it spirals round, almost like water going down a plug hole. But at this point, the gravity gets so strong, it's got nowhere to go except straight into the black hole. But these black holes don't feed smoothly. I might have given you this impression of this constant stream of gas coming in, getting hot and just gently glowing over all time. But these things feed in enormous gulps. You'll start with a very slow trickle of gas coming in. Then the gas will speed up. The plug hole will fill up. And then this is where it gets incredibly hot. This is where it starts to glow with X-rays. This is where we reach 1 million degrees. And then it gets superheated. So the disk of gas that's trying to fall in gets puffed up and blown away. So it can't fall in anymore. It then starts to get dim and falls back to a trickle. So these things go through cycles. These can last a few weeks to a few months and repeat sometimes every year. But in other cases, they can sit quiet for long periods of time. Here's Cygnus X1. Cygnus X1 has a neighbour called V404 Cygni, which in 2015, after being completely invisible, suddenly lit up and appeared. This black hole was last seen in 1989. But in late 2015, it came back and started flashing very brightly, going up and down in its brightness by factors of a few hundred over just hours, and then it died away again. So that's small black holes that are formed at the ends of the lives of stars. What about that giant monster we had in the Cygnus galaxy? Well, it turns out that every single fairly decent-sized galaxy, I'm not counting the little dwarf galaxies here, but it turns out that pretty much every single big galaxy that we see in the universe has what's known as a supermassive black hole at its centre. Now, Cygnus X1 was 15 times the mass of our Sun. A supermassive black hole is between 1 million and 1 billion times the mass of our Sun. We don't know where they come from. That's one of the big mysteries of the formation of galaxies that we still have to solve. How every galaxy got a big black hole in its centre, but we know it's there. And all the best galaxies have one. This is an image, a combination between the Hubble Space Telescope, which looks with visible light, the Spitzer Space Telescope, which looks at infrared light, and another telescope called Chandra that looks at X-rays that I'll come back to in a few moments' time, of the centre of our galaxy. It's pretty crowded in there. There's a lot of stars all together in the centre of our galaxy. But if we zoom in on this bright patch right at the centre and take a look at the stars sitting down there, these are stars. We see them going around in orbits. This is a video put together over 16 years from the Very Large Telescope in Chile. This is 32 million times actual speed. But this is real data from a real telescope of stars travelling in orbits around the centre of our galaxy. Something is holding those stars in orbit, particularly that one whizzing round right in the middle on this very quick orbit. If there was nothing pulling that in, it would just fly off. And if we measure how fast it travels, we know how strong the gravity has to be to keep it there. So we need something 4 million times the mass of our Sun. But also, this star is happily going round in an orbit. It's not colliding with anything. So these 4 million suns worth of material in the centre of our galaxy have to be within the ring that this star is travelling. The only thing that can be that dense is a black hole. And even fairly unremarkable galaxies have black holes. The ring here shows a rather boring galaxy. It's called NGC 1277. Doesn't mean a lot. Doesn't seem very interesting. In what's called the Perseus cluster. This is a fairly small galaxy, but it has the second biggest black hole that we've ever found. It's 10 billion times the mass of our Sun, and it's 14% of the whole mass of that galaxy put together. Black holes form an important part of the galaxy. So let's learn something about them. Let's really scrutinise these black holes and find out what's going on. What is powering those firework displays? We've come a long way since the rocket experiments of the 1960s. Our understanding of black holes has come on leaps and bounds over the last 15, 17 years, with what we call the great X-ray observatories. Today we have 3 real workhorses of studying X-rays coming from celestial sources. This is the Chandra Space Telescope. It kind of works like a typical telescope that focuses visible light. It's got mirrors at the front. These are made of iridium, a very heavy metal, but iridium is able to deflect X-rays and focus the X-rays onto a camera down at the back of the telescope here. And you might be surprised to learn that the type of camera is something called a CCD. It's exactly the same type of detector of camera that you have in your cell phone. But we're using it not to detect visible light, but to detect this high-energy X-ray light. Chandra was launched in 1999 by NASA, and the same year, the European Space Agency launched XMM Newton, which is a similar design, except it's got 3 telescopes instead of 1. And these really are complementary observatories. Chandra produces superb image resolution. XMM Newton's not so good in image resolution, but its 3 big telescopes are like big buckets to collect light. So we can get very detailed measurements of the energy of the X-rays. The energy of the X-rays, remember, is almost like the color of visible light. And Chandra and XMM Newton, these are the same size as the Hubble Space Telescope. These are the same sort of scale of mission as the Hubble Space Telescope. And in 2012, we launched NuSTAR. This is a NASA Small Explorer mission, much, much smaller than Chandra and XMM Newton. It was launched on something called a Pegasus rocket, which is a small rocket that was strapped to the underbelly of an L-1011 aircraft, flown up into the stratosphere. The rocket was dropped and then launched away. This focuses the highest energy X-rays. And to focus high energy X-rays into an image, just like we're used to seeing from a camera, you need a very long distance over which to focus them. So this great boom was actually deployed while the spacecraft was in orbit. This thing had to fit into that small Pegasus rocket. But we're still going. We're still developing new tools. And I'm part of a team here at SLAC developing one of the detectors for what's called the Athena X-ray Observatory. This is a project led by the European Space Agency to create a new X-ray telescope that's 20 times the size of XMM Newton. We're producing the electronics that will read out one of the cameras, that will interpret the signals from one of the cameras on that observatory. And with a bigger telescope, we can collect much more light, which means we get more detailed studies, but we can also look for fainter objects. We can look for black holes that are further away. And one of the dreams of this observatory is to detect the first black holes that ever formed in the universe. So, of course, we've been scrutinizing the black hole in the center of our own galaxy with these X-ray observatories to learn about them. Now, this isn't like the Cygnus galaxy. It doesn't have a great monster with 100 billion solar luminosities coming out of it. It's probably a good thing for us it doesn't. We'd probably be cooked if there was something that bright in the center of our galaxy. But that doesn't mean it's quiet. In 2012, Chandra started a long campaign studying the center of our galaxy, and in September 2013, it noticed this sudden brightening, this flare. What's happening? Well, unlike Cygnus X1, there's not this big stream of gas coming off a star, always going in and being heated in the center of our galaxy. Rather, there are little morsels of gas that our black hole is feeding on every now and then, little bits of gas, maybe even little asteroids. These get close to the black hole, they get pulled in by the force of gravity, and they get shredded and they get vaporized. They get heated up to a few million degrees, and we see them glowing with X-rays. But that's not all. Remember I said that neutron star is like a magnet. It has a magnetic field left over from when it formed. Our black hole also is like a bar magnet. This is iron filings around a bar magnet. And when the gas swirls around, the magnetic field that goes through it can get tied up in knots. So if we imagine these lines of magnetic force as being like elastic bands, if you tangle them up, eventually they'll snap. And that'll release energy. If you ever hurt your fingers snapping an elastic band, you know energy comes out of these things. And that is exactly what heats up the gas. These magnetic fields get swirled around, and they heat the gas. And this is the same process that happens in the solar corona, launching solar flares. And if we zoom in on this cloud here, we find something quite amazing. This cloud of gas around the centre of our galaxy, so the black hole has been masked out in this image. It's where the cross is here. It's called Sagittarius A star. We see all of this gas beside the black hole flickering. What's happening is those flares coming out of the black hole, the X-rays, as well as travelling to us, travel towards this gas. They light up the gas, but it takes about 100 years for this light to travel out. So what we're seeing are the flashes from the black hole 100 years ago reflected in the surrounding gas today. It's actually a process called fluorescence. The X-rays hit this gas, and they cause the electrons in the atoms to move up and down, and they cause it to re-emit the X-rays towards us. But we can be historians of the activity from the black hole in the centre of our galaxy. Some of the most impressive flashes of light from black holes, though, come when we don't just put in little asteroids, little morsels of gas, but we throw something big at it. If a star, one of those stars I showed in the video, is unlucky enough to get too close to that black hole, the star will get ripped apart, its gas will get flung out at 10,000 miles an hour, it'll heat up to millions of degrees, and will produce a very bright flash. This is called a tidal disruption event. But unfortunately for studying black holes, these things are pretty rare. We estimate that in one single galaxy, only one star will get close enough to be shredded every about 10,000 years. Over the last 10 years or so, we've counted 30 of these potential events, stars getting close to black holes in other galaxies. But they don't last very long. This star gets shredded, the gas gets swallowed, and they fade away in about a year. So if you want to catch these, you have to be pretty quick. So now, of course, we need to explain the Cygnus galaxy. Here's Cygnus, and it's not alone. We see a collection. These are all Hubble Space Telescope images of these so-called active galactic nuclei. Cygnus is pretty nearby, so we can see the spiral arms of the stars in the galaxy. But even in more distant galaxies, when we can barely make out the stars, we can still see the black hole in the center shining brightly. What we need to power these is a continuous stream of gas, not just little morsels of gas, and not just one star every 10,000 years. If that black hole has got a huge amount of gas surrounding it, potentially the leftover gas from when the galaxy was forming in the first place, that can be pulled into the black hole, and that is what can power these incredible light sources. We see the hot X-rays coming from the disk of gas coming in. We also see the magnetic fields. Those magnetic fields get tied up, and they produce this thing called a corona. And this corona is what's responsible for the vast majority of the X-rays coming out of these big black holes in the centers of galaxies. And a large part of my own research is trying to find out exactly how these systems are powered. What is causing that gas to heat up? And what about that gas is letting it tangle up these magnetic fields? What about that gas is firing particles away to launch these coronae that we're seeing? Well, of course, the light that we see coming from these disks of gas coming into black holes has to travel through the strong gravitational pull of the black hole itself. So what might actually in real life be a flat disk of gas coming in, the light that we see coming from that will be distorted and it will be bent by the black hole. Because the gravity is due to space curving, even light has to follow the path. So in reality, these things are so small and so far away, we just see them as single points of light, like stars on the sky. But I've created a simulation that if we had an ideal telescope and we could resolve an image of these, what we might see. And this is what that disk would look like. If any of you have seen the movie Interstellar, some of these shapes might look familiar to you. So the distortion of this image is apparent. What we see up here, this is the backside of the disk that would be hidden behind the event horizon, but that light is being bent up over the black hole and towards us. That's the equivalent of you being able to see my feet as I stand behind this podium, just by the light being bent over it. And the material in this disk is travelling round at half the speed of light. And when material travels that fast in a strong gravitational field, the bit that is coming towards us, we see it shifted to higher energies, and we also see it getting brighter. If you have a light bulb travelling towards you at half the speed of light, you won't see it shining in all directions. You'll see it push the light it emits out in front. And you will see the light shifted to higher energy. You will see it look bluer than it really should be. And the opposite is true on the other side. It shifted to low energies, it looks red, and all of that light is sent away from us, so that side of the disk looks dim. And even though we can't see these images, we can measure this effect. So we were fortunate last year to get the longest ever observation with XMM Newton of one single black hole in the centre of our galaxy. And this is kind of what it looks like. I won't bore you with the details of this, but we can see the spread of the X-ray energies coming from the disk. We see parts of the X-rays becoming more red and parts of the X-rays becoming more blue. This shape is a unique signature of the strong gravity around the black hole. And of course, we keep an eye on black holes. NASA's SWIFT satellite, originally designed to look for explosions called gamma ray bursts, it has a big detector on it that can see a large fraction of the sky at once. If it sees a flash, it quickly goes to look at it. But when it hasn't seen a flash, we don't let it waste its time. We just get it to visit our favourite black holes, visiting each one once a week, maybe once a day for the more interesting ones. And one of our targets that we were monitoring, called Markarian 335, SWIFT saw it brighten by a factor of 10. So as soon as we saw this, we asked the director of the New Star Observatory if we could point New Star at it to get a real close look at what's going on. And the findings were quite incredible. By looking at those energy shifts I just showed, the red and the blue shifts in the light coming from the disk, we were able to see that the corona, those hot particles flung up by the magnetic field producing X-rays, had become gathered up around the centre. They'd been shot out, almost like this is trying to form a jet. But it failed. It collapsed away and died back down again. This is the first time we've ever really seen something being launched away like a jet from a supermassive black hole. Even though we've known about jets themselves, continuous jets that always look like this, that are steady since the 1960s. We saw this flashing and trying to launch one of these jets. And these jets these continuous jets are worth talking about for just a minute in their own right. This is another galaxy. This is called Cygnus A. It's a fairly unassuming looking galaxy if you look at it with the visible light. But just bear in mind how big that galaxy is in the middle of the image. If we now look at the X-rays, we see there's a lot of hot gas. There's the galaxy. We see lots of hot gas. There's something going on heating the gas around this galaxy. And what that is revealed by the radio waves. Radio waves are produced when electrons start to dance around. We produce radio waves to communicate with our cell phones with electrical circuits that move electrons. What's happening here is the black hole in the center of that galaxy is launching electrons at almost the speed of light in these jets that are tens to hundreds of times the size of the whole galaxy. These electrons in the jet are dancing around. They're producing radio waves that we can detect. And these jets slam into the gas around the galaxy. They blast out these giant cavities and blow these enormous bubbles in the gas between the galaxies, all powered by a black hole right at the center. And the energy output of these jets is enormous. The total energy output from a black hole, all of the light and all of the kinetic energy that comes out of these jets, if you just do a quick back-of-the-envelope calculation, it turns out it is equivalent, it is the same amount as the gravitational energy keeping all the stars in the galaxy. That means if you could take 100% of the power output of a black hole, feed it into all the stars in a galaxy, you would blow the galaxy apart. But more realistically, we think about the black hole growing with the galaxy. As the galaxy gets bigger, the black hole starts getting stronger in its jets and in its emission. So as the black hole gets bigger, as the galaxy gets bigger, the black hole starts to push the gas away. So the galaxy that is growing from the gas around it then starts to have its gas supply pushed away by the black hole growing in the center of the galaxy. We can see this in the Perseus cluster. We zoom in on the bright galaxy right in the center. Here is the visible light image. We see these filaments of hot gas. Again, a clue that something's going on there. But now, if we add the radio waves in purple and the hot X-ray gas in blue, we can see what these jets from the black hole in the center are doing. The jets come up, they heat the gas, they blow bubbles in the gas, and they push the gas away. This is just a zoom in on just the hot gas with the X-rays. We can see the bubbles being blown by the black hole right in the center. So think of a supermassive black hole not as a great monster, but think of it as a sculptor, gently guiding the growth of the galaxy around it. And just for a size scale, this is the equivalent, the black hole in the center of this galaxy and this gas around the galaxy, this is the equivalent of something the size of a grape controlling something the size of the planet Earth. Black holes are not just astronomical ornaments. They played a vital role in shaping the structure of the universe. And if we want to understand how everything formed and how it evolved into what we see today, we need to understand what happens in the final moments just before material falls into a black hole, and how the impressive jets, flares, and firework displays are powered. I'll stop there. Thank you.
So thank you very much, Dan. We have time for questions. You all have those microphones in front of you, but only one works at a time. So raise your hand, get recognized, turn on your microphone, and ask the question. Who'd like to go first? Sir. Oh, I'm sorry. Yeah, go ahead.
I believe it was this month's Scientific American, there was an article about primordial black holes, and The implication was that they were responsible for dark matter. Can you comment on that?
Oh, so dark matter is one of the biggest mysteries in astrophysics today. If we look at the gravitational force that holds galaxies together, we can't account for how much gravity there is by the amount of matter we can see in the stars. So primordial black holes are these black holes in the centers of these galaxies, or black holes elsewhere in the universe that formed very early on. It seems unlikely that there's enough of them to explain dark matter. So there's ways we can trace how many primordial black holes we think there are, how heavy they are, just by looking at all the light we see from them today. We can sort of run that calculation I did at the beginning backwards. We can see how much light there is left over from these black holes as they grew. We can turn that into how much material must be in these black holes. It doesn't seem like we can balance the books with the amount of dark matter we need and having black holes, having it all in black holes from the early universe, unfortunately. So it's a nice idea, but unfortunately we need a little bit more than we can account for.
Thank you. When we're talking about, for example, the photo that's up on the screen, we talk about something that's a round ball of gas, and it collapses into a black hole, right? And I'm just trying to think, why do we suddenly go from a round structure to what seems to be a disk shape when, if you're talking about a hole, why isn't it just sucking from all sides?
Okay, so that's actually a very good question. So there's a law in physics called the conservation of angular momentum, which says that if something starts rotating, it has to keep rotating. So right in the beginning, we've got this big spherical cloud of gas. And just by random chance, so the gas is moving in all directions, but by random chance, there's maybe a slight bit more motion in, say, this direction, but only very slowly. But as it collapses, conservation of angular momentum requires that to keep the same angular momentum, this thing that's moving very slowly at a large distance has to get faster in its rotation as it comes in. So this slight rotation gets amplified. So then what happens is you've got this random movement of gas with this extra bit of rotation in this direction. The random movement means for every atom moving this way, there's one coming up the other way to collide with it. So something coming down, something coming up, they collide and they end up stuck in the middle. So what you end up with is this thing flattening, but keeping this slight random rotation it had at the beginning. Does that make sense?
I know this isn't history of science, but you said it was in the 18th century that dark stars were hypothesized. But at that time, it wasn't understood that there was a upper limit on velocity, nor was it understood that light was influenced by gravity. So it would be, a dark star was defined as something from which no mass could escape?
So there were very early ideas of the finite speed of light just by measurements that had been taken across the solar system. So they didn't know that it was the ultimate speed limit, but they started to get an idea that light wasn't traveling instantaneously. So it was just thinking of something that was keeping light at the finite speed they knew it must have. They were just thinking about something that could be keeping light down, was the idea.
Could you elaborate more on how the black holes at the center of the galaxies guide the evolution of the galaxy? The statement that you made at the end.
Okay. So this idea, so there's a lot of evidence for this so-called coevolution. So the first line is, as I said, there's this, we can very easily calculate that all this energy coming out is enough to blow the galaxy apart. So we're starting to see it can have a profound effect. Also, by measuring very accurately, we can measure the mass of black holes by looking at the stars traveling around them. We can also measure how fast the stars travel in the bulge in the center of a galaxy. So we can, and when you start comparing how big the bulge is in the center of a galaxy, how fast the stars are traveling in that bulge, with how big the black hole is, we find very tight correlations. So not just that it's a bigger galaxy, so just it's bigger, so we expect it to have more stars and have a bigger black hole. It's much too tight a relation to just be sort of a coincidence. So there's a lot of lines of evidence that there is this feedback, it's called, between the black hole and the galaxy. So the working hypothesis is that so I said, we don't fully understand how the supermassive black hole got into the center of the galaxy. But we can think of it forming as the galaxy grew. So the galaxy starts as a big cloud of gas, and gravity pulls it together. So it clumps up in the outer parts, and that's what forms the stars. But towards the center, the force of gravity gets stronger, so more gas gets pulled towards the center. So you end up with a lot of gas being pulled in. So either that gas in the center just got directly squeezed together, kept getting compressed, formed a black hole, and then as more falls in, it heats up, it launches jets, it goes through all the firework displays that I showed. So then as the galaxy gets bigger, the black hole gets bigger, its energy output gets stronger. So then just the sheer power coming out of it then starts pushing the gas away that's trying to fall into the galaxy. So then as the galaxy gets bigger, the output from the black hole gets stronger, it pushes more gas away, so that slows down how quickly the galaxy can grow. So this black hole is sort of guiding the gas into the galaxy, stopping the galaxy growing too big.
So the Andromeda galaxy is set on a collision course with us. So what happens when two, like in billions and billions of years, but what happens when two supermassive black holes at the center of galaxies collide with each other?
So that's actually very interesting. And so one of the hot topics of research at the moment, so these things are called active galactic nuclei, or AGN, where you have this bright black hole glowing in the center of a galaxy. So one of the hot topics at the moment is looking for dual AGN, where you don't just have one black hole in the center of a galaxy, you have two black holes. So the idea is when the galaxies collide with each other, normally the stars in a galaxy are so far apart that the stars don't actually collide. What you end up with is, it's just like having a bag of sand and another bag of sand and throwing them together. So the grains of sand don't merge together. You just end up with this bigger galaxy that's formed from all the stars of the two that collided. But the black hole in the center of a galaxy will work its way, will go through the center, and it'll be attracted by gravity to the black hole in the other galaxy. So these two black holes come together. Now, all this stuff that's going on, that's throwing stars, throwing gas around as the galaxies merge, that could send a whole lot of gas into the center of those black holes. So even if, like our black hole, they're sitting there quietly not feeding, they could feed and light up again. So that's one thing that could happen, is we could start seeing these two black holes glowing again, just like these active black holes that I've been talking about today, but we see two of them. But then these black holes will be in orbit around each other, so we'll end up with what's called a binary black hole. And binary black holes, when they go around in orbit, emit gravitational waves. So the gravitational wave discoveries that have been made by LIGO were where two black holes in orbit around each other, gravitational waves come out, that carries energy away from the system, so that causes the two black holes to spiral into each other. They start falling towards each other. So then we'll see gravitational waves coming out, and then they'll merge into one big black hole. So you then end up with this, instead of these nice, neat spiral galaxies, you'll end up with this big sort of blob galaxy. We call it an elliptical galaxy with a big black hole in the middle of it.
Lots of kids in the audience. Any of you guys want to ask Dan a question? Sorry? Please.
Do humans have knowledge of what happens if matter makes contact with the singularity of a black hole?
Oh, we don't. So that is a very interesting question. So we know what formed the singularity, what formed the black hole has been squeezed together so much. You've got something made from a star, or millions of stars, that has been squeezed into something so dense, it's more tightly packed together than what's in the middle of an atom. So you've got something that's the size of a star being compressed smaller than protons and neutrons. So it can't be made of matter as we understand it. It's something weird, it's something we don't know. But unfortunately, no light can get out of the event horizon. So we can't see anything that's going on in the middle. So we sort of have to dream up theories, but we have no way of seeing what turns into it, unfortunately.
So let's take one last question. Ma'am?
So I'm assuming that a lot of what we understand of the universe is based on traces of history. And we're sort of putting things together based on that trail of history that we see out there. And I'm assuming that we, as a planet, also have a history, and we leave a trace behind. Are we studying our traces of history as a planet, and how do we know we're not in a black hole?
Well, we could very well be stuck inside something else that nothing can get out of. I mean, we have no way of knowing that. But you are quite right. I mean, we're looking at the history of the universe, and we're sort of trying to understand what happens by sort of piecing together the little bits of information we get. But as you say, we have our own history as well, our own culture and our own theories that we've already had. So there's always this interesting interplay between trying to understand the universe and science and sort of the understanding we've got and the culture we've got. I mean, I always like to think about physics as we're not, when we come up with these ideas like general relativity, general relativity is itself an equation. It's numbers. But it just so happens that they're numbers that when you play with them, they behave in the same way as we see things happening around us in the universe. So we're not directly sort of seeing the universe, we're sort of building models to try and understand how it works. So what we do is we sort of have our model, which is the universe as we understand it at the moment, that is sort of influenced by everything we thought we knew in the past. And then we'll see something, and then if it fits with our model, great. But then if it doesn't fit, we then have to sort of refine our model. So we're always trying to build a better sort of duplicate of the real universe to try and understand it. But yes, we're tracing our own history as well as the history of the universe, and it's very much biased by the information we can see and what we thought we knew before. So it's a good question.
So let's thank Dan very much. We look forward to seeing you at the end of September. We'll have the next one of these. Those of you who'd like to ask Dan more questions, he'll be outside in just a minute, and we'll see what else you'd like to know. Thank you very much.